Assalamu alaikum and good morning, everyone. Today we're going to continue with your topic 7, equilibrium. And our next section is factors affecting Kc and Kp. So you have already covered equilibrium constants in terms of concentration, Kc, and in terms of partial pressure, Kp. At the start of this section, I have mentioned that there are some factors that don't affect the change in Kc and Kp value. Now, because they are equilibrium constant, you may think that, okay, changing concentration will not change the constant, changing pressure, adding catalyst, or yeah, they will not change the value of the equilibrium constant. Only one factor will change or will affect the value of our Kc and Kp, and that would be temperature. Exam questions will be tempted to trick you, and you will be tempted to fall into the trap of thinking that increasing concentration of either your reactant or your product would affect the value of Kc and Kp because they are numbers, and you expect if you play with the concentration, then the Kc and Kp will also change. And that only happens to temperature. Okay. So these other factors will not change the values of Kc and Kp. It will change the equilibrium position. However, the value will stay constant, right? Remember that changing the temperature, changing the concentration or pressure will change the position of your equilibrium depending on the change, depending on your system as well, but will not change the value of equilibrium constant. So we're going to look at Kc and the temperature changes. So this is a system of equilibrium. If it's in a dynamic equilibrium, we should assume that it is in a closed system, and the enthalpy change of this system is positive 10 kilojoules per mole. This means that because it is an equilibrium, we have a reversible reaction. That means the forward is endothermic, and the backward or the reverse reaction is exothermic. It has the same size but different sign. Okay, so that's -10 exothermic reaction for the backward or reverse reaction. Okay, if we write down the Kc expression, it will be the concentration of the products. In this case, our products are hydrogen and iodine over the concentration of our reactant raised to the power of its mole ratio. Okay, so that would mean concentration of hydrogen iodide to be raised to the power of 2, or we say that square. The value of the Kc equilibrium constant is 6.25 times 10 to the power of -3, and there's no units. You already know how to work out the units of each Kc or Kp expression. So that's the number of Kc at 500 Kelvin. Okay, if you bring your attention to the table, you can see that this table contains different temperature and different Kc values. You would notice that as you increase the temperature from 300 to 1000, the values of your Kc increases as well. Okay, so we're going to look at this, right? So remember, Kc is concentration of products over the concentration of reactants. Right? This is important because you will first have to look at the effect of changing temperature on the position of the equilibrium. All right, let's have a look. For the system, we want to look at increase in temperature. Okay, you can look at decrease in temperature or increase in temperature, but I see it as it's easier to look at the increase in temperature, so the numbers increases as well. Okay, so yeah, I don't want to draw in the arrow. Right, so what happens when I increase temperature? That means my system wants to reduce the temperature, correct? In order to reduce the temperature, the endothermic reaction has to be favored to take in the extra heat, to absorb the extra heat. So what happens is that endothermic reaction is favored. Okay, so that's the forward reaction. Endothermic reaction is favored, which means you have more products in your equilibrium, right? Now, if you carry that qualitatively, okay, that means without using numbers, more products over reactants. If you look at the Kc, you have products on top and reactants at the bottom. So if your product is big, your Kc will also be big. Okay, so that, I hope, explains why increasing temperature will increase the Kc for this system. Of course, if you're looking at a different system where the enthalpy change is exothermic for the forward reaction, that means the opposite will happen. Increased temperature will decrease or reduce your Kc values, right? Okay, so please copy this down. What happens to when you increase the temperature? And if you want to copy this down, you can pause it, okay? Okay, next we're going to look at example. This time we have a system of sulfur dioxide reacting with oxygen to form sulfur trioxide. So this is the dynamic equilibrium system for the production of sulfuric acid, contact process, okay? And the enthalpy change of this reaction is negative. That means forward, it's exo, and backwards is endo, right? What happens to the value of Kc when temperature is increased? Okay, let's have a look. Okay, so I'll just explain to you briefly first, okay, before we look at the next page where I will ask you to copy down in nicely formed sentences, okay? Right, so what happens when temperature increases? Endothermic is being favored. And you can see that endothermic reaction is our reverse. Equilibrium shifts to the left. If your equilibrium is shifting to the left, you now have more reactants than products. And if you remember, Kc is proportional to the concentration of products over the concentration of reactants. If your reactants is big at the bottom, on top stays the same, or we say small, then of course your Kc will decrease. All right, that's how you see it, because we now have big reactants. So bottom number is bigger. That means Kc must be smaller. Okay, that's how your thought process should be. But when putting it in words, we say the reaction will shift to the left in the backwards endothermic direction to oppose the change. The position of equilibrium shifting to the left means more reactants form. Therefore, value of Kc will get smaller. Okay, so please pause this if you want to copy this down. I will move on. To determine increase or decrease in Kc or Kp, remember this only applies to change in temperature. First, you must look at which reaction is being favored, forward or reverse. And then you look at the equation that is being favored. Are you increasing the reactants? Are you increasing the products? And then remember this expression where your Kc or Kp is proportional, okay, to your products over reactants. So more products, big Kc, more reactants, small Kc. Okay, moving on. We are now moving away from Kc and Kp. We want to describe and explain the constant conditions used in the Haber process and the contact process. Now, I am sure you are all familiar with these two processes already, but now I want to explain why we use the conditions. Maybe in O-level you have learned the conditions for each of these process to work at optimum rate. Okay, at optimum means at the best or at the maximum rate. Okay. So the next section is called the equilibria and the chemical industry. Looking at the production of ammonia, which is called the Haber process, you already know that we combine nitrogen and hydrogen together in the ratio of 1:3 because of the mole ratio to form ammonia. Okay, and then the conditions are 400 degrees Celsius, 200 atmosphere, and we use iron catalyst. Okay, and then of course at the end of the reaction there will be some reactants, some gases that are unreacted, so we just recycle them back into the reaction system so that it will finally react. And then also in this process, whenever we produce or form ammonia, we always remove the ammonia after it has been we turn them into a liquid, okay, so that they are being removed out of the equilibrium or the system, right? So remember, this process is a reversible, it's in dynamic equilibrium. So removing ammonia, if you can see here in the equation, that means you are decreasing ammonia. So if you decrease the concentration of ammonia, what will happen is that your forward reaction will be favored. Le Chatelier's principle said that if you reduce ammonia, my system will increase the value of ammonia. Okay. All right. First, we look at the pressure. Why is it that we use the pressure of 200 atmosphere? Okay. Now, increasing pressure, look at this system again. On the left, you have 4 mole. On the right, you have 2 mole. Based on the Le Chatelier theory that we did last few lessons, okay, increasing pressure, the system would want to decrease the pressure, all right? So it favors towards the side with the less number of molecules. That means forward reaction is favored. So you want high pressure to produce more ammonia. That's our goal. That's our aim, to increase the yield of ammonia, okay? Because we're in a system of production of ammonia. We do not want to produce nitrogen and hydrogen. And remember that this system is reversible system. Ammonia can always break down into its original reactants, okay? But by increasing pressure, hopefully that will push the equilibrium to the right so that only forward reaction happens, okay? But not 100%, although there will be some reversible reaction happening as well, but majority will be the forward reaction, okay? That means favoring forward reaction will give you a very high yield of ammonia. That's the reason High pressure will give high yields of ammonia because of the increased pressure, shifting the position of equilibrium to the right. Okay, so this is important. Secondly, high pressure also increases the rate of reaction. We haven't learned rate of reaction yet. That is kinetics. The reason why increasing pressure will increase the rate of reaction is because you are also increasing the frequency of the reactants to collide and to have a reaction. Okay, that will be covered in the next lesson. So usually we look at yield, how much we're getting, rate, how fast we are getting ammonia, and lastly is the cost. Of course, building a plant or a factory that can withstand high pressure is not cheap, it's expensive, right? So 200 atmosphere is just fine, even though that's really high. That's 200 times the normal atmospheric pressure, okay? So we don't want it to be too high because this would result in a higher cost and maintenance of equipment, okay? So high pressure plant or high pressure factory is usually very dangerous, okay, because you have this fear of it exploding. So high pressure is not always, not problematic. There will be some problems and risks to have a plant or an area that can withstand high pressure. Next, we talk about the temperature. Okay, we want a high temperature, but also not too high, right? It has to be a compromise. So let's have a look at this system again. What happens if I increase the temperature? Okay, first we look at the enthalpy. Forward is exo, reverse is endo. Okay, increasing temperature will only favor the endothermic reaction, which is the reverse. This is not what we are aiming for. We want to produce more ammonia, not reactants. Okay, so that's why too high of a temperature would be a problem, because you are just pushing the equilibrium to the left. If anything, you want to push the equilibrium to the right. It just happens that the system has an exothermic reaction forward, okay? But the good thing about high temperature is that it increases the rate of reaction, okay? Okay. Low temperature should give high yields of ammonia. So we're looking at the yield. We're also looking at the rate. So that's the rate of reaction. And the cost is not mentioned here, okay? So too low temperature would give you the best yield. However, too low of a temperature would make your reaction go really, really slow. So it's a compromise. You want fast reaction, but low yield, or high yield, but very, very, very slow reaction. So as a result, we have a compromise at about 450. So this is called a compromise. A compromise temperature of 450 degrees Celsius is used to speed up the reaction and also to get an ample amount of yield ammonia. All right, so you should be able to explain why we don't increase the temperature way up high, or why we don't reduce the temperature way too low. Next is using a catalyst. Okay, remember that catalyst does not have any effect on the yield. It does not favor forward reaction, nor does it favor reverse reaction. Actually, it favors both forward and reverse, but it doesn't have any effect. Okay, so adding a catalyst will only increase the rate of reaction, and that's okay. We're looking at the kinetics point of view. Ammonia is removed by condensing it to a liquid. So this was what I was saying just now. What happens in this plant is anytime you produce ammonia as a gas, they remove it out of the system. The reason for this is that if you remove ammonia out of the system, that means you are decreasing or reducing the concentration of ammonia. Le Chatelier principle would say, okay, if our ammonia is now small, we have to increase it. And how do we increase it? By producing more, by favoring the forward reaction. Okay, and this is good. We like if the equilibrium is favoring the forward reaction. That means you are getting more and more ammonia being produced, increasing your yield. So equilibrium actually is talking about the yield of your product, how much product you are getting. If you are favoring to the product side, you get more product. If you are favoring the reverse side, you get less product. You get less product, but more reactants. Usually it's a bit silly to get more reactants. We want products, okay? Depending on the system and depending on the ideal, what you want to collect, okay? Next is the production of sulfuric acid, which is called your contact process. So I will just go through briefly the system, okay, how it works. I will not explain in details, but I will explain to you why the conditions are being used. Okay, so this is a system of a simple diagram to show the system of the contact process where sulfur dioxide will combine with oxygen to form sulfur trioxide. Okay, so this is just a part in the production of sulfuric acid. If you want to convert the sulfur trioxide into sulfuric acid, you have to first dissolve it in 98% of sulfuric acid, where you get oleum. Okay, and then this oleum, you dissolve it in water to get your sulfuric acid. For this system, usually the efficiency of this reaction is 99.5%. That means if you have 100 moles of reactants, 99.5 of it will be converted into products. So it's very efficient, right? The reaction is naturally efficient. The reason for this is maybe because of the activation energy is quite low. So many of the reactants can just convert into product. Temperature, moderate temperature of about 450 degrees Celsius. Again, it's quite low of a temperature. Usually high temperature would be around thousands. Okay, so why don't we increase the temperature all the way? Because high temperature will increase the rate of the reaction. It's great. You want to form your products real quick. Okay, the reason is, again, if you look at this system, equilibrium system, it has an enthalpy change of -197. That means the forward is exo and the backwards is endo. So increasing temperature, if we increase temperature, that means the system would want to reduce it. Endothermic reaction is favored to take in the extra heat. Now, if we are favoring endothermic reaction, look at my arrow. It is favoring to the left. We are producing more reactants. So we don't want it to be really high. Okay, and then you may say, then why don't we go really, really low? Now, if your temperature is super low, your reaction will be really, really slow. Okay, we are talking about commercial production here. You want to produce product at such a short time. You don't want to take, you really don't want to compromise on the time of the reaction. Okay, so 450 is about like in the middle. It's a compromise between the yield and the speed of the reaction, just like your ammonia. Okay, you can read this. I will move on. Atmospheric pressure. Now, they don't use high atmospheric pressure. Actually, they don't need to use high atmospheric pressure. The reason is because this reaction is already efficient. Okay, you have a 99.5%, that's close to 100% conversion. And that means you don't have to waste your money on building a plant that can withstand high pressure. You can just use normal pressure. At normal pressure, the conversion rate is still great, 99.5. Okay, so very high pressure is unnecessary for this process. Yes, you can, but companies would rather not. Sorry. Okay. Lastly is the catalyst. Again, for the same reason like your contact process, the catalyst is added to increase the rate of the forward and reverse reaction. It favors both the forward and the reverse reaction. No net effect. Okay, no net effect on the yield. It just means that you get your products very quick, right? That's why we use catalyst. Okay, so that's the industrial process and the equilibrium system involved in the production of ammonia and sulfuric acid. Next, we want to look at the next section of your equilibria. It's the ionic equilibria, which is where your acids and bases come in. So this is called the Bronsted-Lowry theory of acids and bases. Okay. So for your first learning objective, you are to state the names and formula, only limited to this list, but I know you know that Cambridge will like to give you a surprise and give you an acid that you have never seen before and never been mentioned before. Okay, state the names and formula of the common alkalis limited to this: sodium hydroxide, potassium, ammonia. Okay, again, we know that's not true. Right, definitions of acids and bases. There are a few definitions of acids and bases depending on the theory you are using. If we talk about acids being a species that release hydrogen ions in water, this is called the Arrhenius definition. Arrhenius is a person, and this is his theory. Acids and bases are in terms of H plus and OH minus ions when it dissolves in water. Okay, so there's nothing new for you. The only thing for you here is the Bronsted-Lowry theory, which is talking about acids and bases in terms of proton. Now, I want to talk about this hydrogen ion. Okay, hydrogen, if you look at your periodic table, where's my periodic table? Okay, so you look at hydrogen here. Hydrogen has an atomic number 1, that means 1 proton. It also has a mass of 1, which comes from the proton. That means hydrogen does not contain neutron, hydrogen. Okay, so hydrogen is when you have 1 proton at the nucleus, and then you have 1 electron. Yeah, this is a hydrogen atom. Now, when you lose hydrogen to become H plus, okay, hydrogen atom to become hydrogen ion, H plus means you have lost the electron, right? So no more electron circling outside your nucleus. That means you are only left with your nucleus, which is a proton. That is why hydrogen ion is called a proton. Okay, so H plus is actually a proton, just a proton, because you have lost your electron floating outside and you're just left with proton in your nucleus. There's no there is no neutron in a hydrogen atom. Okay, moving on. I will revisit the Bronsted-Lowry theory later on. I want to define acids. Acids release hydrogen ions when they dissolve in water. Bases accept hydrogen ions or a compound that contains oxide or hydroxide. Sorry, I forgot to define Bronsted-Lowry. Acids donate protons, bases accepts protons. All right. So how? Later we have a look. Okay. So these definitions given to you in the box are based on Bronsted and Lowry theory. Do you have to learn their names? Yes, because sometimes question will ask define acids and bases in terms of Arrhenius definition. And if your definition is not in terms of H plus and OH minus, then it will be wrong. Okay, so these are the name of acids that Cambridge say you have to learn, only this, but you will come across other acids later on. HCl, hydrochloric acid, and in ions, they form H plus and Cl minus. Okay, nitric acid is HNO3. Remember, this nitric acid is +5, right? And O3 minus. Okay, +5 is the oxidation number. So the ions that it will form in water would be H plus and NO3 minus. Sulfuric acid is H2SO4. Remember that there are 2 protons, 2 moles. This one is called a diprotic acid. That means diproton. There are 2 protons here, 2 H plus. Okay. So if you break this down into ions, you have 2 lots of hydrogen ions and a sulfate ion is of SO4 minus. Ethanoic acid is your organic acid. It falls under your carboxylic acid. You know the formula of ethanoic acid already. And in water, they form hydrogen ions and ethanoate ion, CH3COO minus. Okay, if you don't remember this, you have to revisit your carboxylic acid. Next, bases are species that accept hydrogen ions or a compound that contains oxide or hydroxide ions. So you see this, accept hydrogen ions, that's Bronsted-Lowry definition, right? Contains or give away oxide and hydroxide ions, that's Arrhenius definition. So you really have to follow the question if they are specific. If they don't mention whose theory, then you just choose one. These are the common alkali. Now, what's the difference between a base and an alkali? An alkali is a soluble base. All alkalis are base, but not all base are alkali. Okay, so base is like the big group, and then the alkali is a smaller group. Those soluble ones fall in or under the alkali. Sodium hydroxide, the formula is NaOH. In water, they form ions as Na plus and OH minus. Potassium hydroxide, KOH. In water or in aqueous form, they exist as K plus and OH minus. Ammonia, aqueous ammonia, well, we know ammonia as NH3 gas, but the aqueous ammonia is actually, so maybe this is the only thing that's new for you, NH4 plus and OH minus. So aqueous ammonia is actually this. Okay, but sometimes, of course, we write it as NH3 aqueous. But the ions are NH4 plus and OH minus. So you have to, this is something new for you, okay? Next, Bronsted-Lowry theory. Okay, so I will go into details on this Bronsted-Lowry theory. The Bronsted-Lowry theory defines acids and bases in terms of proton transfer. True, right? Because acids donate the protons, bases will accept this proton that comes from the acid. So this means we are transferring proton. Especially, we're talking about acids and bases in a reaction, of course, okay? So when acids lose their proton, when they lose their hydrogen ions, the base or the alkali will accept or will take this hydrogen ions or protons from the acids. So that's what we mean by proton transfer. When an acid or base reacts with water, an equilibrium mixture is formed. This is why we talk about acids and bases being an ionic, an example of an ionic equilibria, because when we dissolve it in water or we react it with water, there is an equilibrium mixture. That means the forward reaction is happening, the reverse reaction is happening, okay? For example, hydrogen gas chloride dissolved in water to form hydrochloric acid, okay? So you can see here, I'm just going to show you quickly the proton transfer. If you look at your reactants, the hydrogen, H plus, the protons is on the HCl, correct? It is on the acid. Your acid will lose this H plus and give it to water. So you see in the product, your chloride, sorry, your HCl is now becoming a chloride and your water is now becoming what we call a hydronium or hydroxonium ion. Okay, so I will show that to you in detail in the next slide. Okay, so there's a lot of things that I want to talk about this part, okay? Oh, I forgot to mention actually just now on the first page. Never mind, I'll mention it to you the next time. Right, so what happens is hydrochloric acid is acting as a Bronsted-Lowry acid. Bronsted-Lowry acid usually gives away its H plus, right? Now, if you look at HCl in terms of heterolytic fission, okay, heterolytic fission, what happens is that the electrons will go, the electrons will go to the more electronegative atom, which is now your chlorine. So that's why hydrogen did not receive the electron, so it becomes H plus. Chlorine has received the electron, so it now becomes Cl minus. Okay, so that's why when you lose hydrogen ions from the HCl, chlorine will now become chloride. Just add in your electrons. And then look at water. Water is H2O with the lone pair on the oxygen. Okay, now look at water. Water now accepts the hydrogen plus. So if water is a neutral molecule, H2O, plus a H plus, it becomes H3O plus. Yeah, this came from acid, which was your HCl just now. And this H3O plus is called hydroxonium ion. All acids, when dissolved with water or dissolved in water, will have this hydroxonium ion. It is the equivalent of our H plus. Okay, hydroxonium ion is sometimes called a protonated water. Why? Because your water has accepted a proton, has received a proton. If you notice, even though I have charges on both sides, sorry, on the right side, on the left side, no charges, neutral, right? On the right side, I have charges, negative and positive, but nicely they cancel out. So overall, my equation is balanced and also neutral. Okay, if I were to write this down in equation form, I will write it like this. Maybe you want to color code them. Okay, do I? Okay, never mind. No need to color code because this one is already color coded. You can change your notes if the colors don't appear. HCl gas reacts with H2O liquid to form Cl minus, oh, sorry, it should be a reversible. Cl minus, now it's aqueous, plus H3O plus, and that's aqueous. And this is called a hydroxonium ion, right? This is the equivalent of writing HCl gas when we dissolve it in aqueous, now becomes H plus and Cl minus. Can you see that the H3O plus is actually the equivalent of your H plus, right? This is your O-level way of writing down the dissociation of HCl. This is the A-level, or we say the Bronsted-Lowry theory, because you can see that HCl becoming a Cl minus has donate its hydrogen ion to H2O, which turns into H3O plus. Next, it works with bases as well. Same thing, but notice that even though water, we don't usually define water as acids and bases, right? But because water is already accepting a proton, it now becomes a proton acceptor, which is a base. Next example, we look at ammonia when it reacts with water. Again, notice that ammonia goes to form or becomes NH3 that has accepted a H plus. In this case, ammonia is a proton acceptor, whereas your water is a proton donor. You can see that H2O has lost its H plus. Same thing. How does that happen? H2O, the bond breaks heterolytically to form H plus and OH minus. So there's a lone pair on the oxygen. Okay, so you can add in the lone pair of electrons there. So this is how ammonia and water is acting as Bronsted-Lowry base and acid respectively. Okay, so yes, acid can behave as a base or as an acid depending on who it is reacting with. If it reacts with an acid, it becomes a base. If it reacts with a base, it becomes an acid. Okay, I want to talk about the product of the acid. This is now, if you can see, is NH4 plus. Okay, so that's H plus plus NH3 to become NH4 plus, and this is called ammonium ion, NH4 plus, right? If I were to write this in a normal equation, H2O liquid plus ammonia gas with the reversible arrow because it's an equilibrium, OH minus plus NH4 plus. Remember just now when I mentioned formula of aqueous ammonia, NH4OH. Yep, this is aqueous ammonia. Okay, and you cannot possibly show this if you didn't have the water in the expression or in the molecule. Okay, like this, NH3. Okay, what do I form? OH minus. Suddenly, where am I getting the OH minus from, right? So that's why you didn't learn about the equation of dissociation of ammonia before this, because you need water in that expression, because otherwise, how would you define ammonia as a species that releases OH minus if it didn't react with water? NH3 could not possibly break down into OH minus and NH4 plus, right? Okay. So Water is called an amphoteric because it can act as a Bronsted-Lowry base or Bronsted-Lowry acid. As you can see, when it reacts with an acid, it becomes a base. When it reacts with a base, it becomes an acid. And it has to follow the Bronsted-Lowry definition. It will either accept proton or donate proton. Next is just showing you the gas phase. Can Bronsted-Lowry be shown in a gas phase? Can. So HCl is your acid. Acid will donate its proton. Okay, so that means HCl would become Cl minus, and then NH3 will gain that hydrogen ion. So I don't really like the equation here. I would change this. Okay, I would redraw that. How do I do that? Redraw that into so that you can see what's happening. Oh, because we're talking about gas, that's right. And then the product is a solid. Okay. I will draw the product, but without the state symbol. Okay, because otherwise you'll get confused. So Cl, my Cl is now Cl minus. And do I have space for this? I have NH3 with that's not right. Sorry. With my hydrogen. So I'm just gonna draw a small hydrogen, not nitrogen. Hydrogen plus. So you get Cl minus and NH4 plus. Okay, so I'll leave out the state symbol because if it was a solid, I wouldn't be able to draw it as an ions. Yeah. Right. Okay. So in the product, then you can see that the HCl has lost its proton and H3 now has gained a proton. So hydrogen chloride must have been an acid proton donor, and ammonia must have been a base that is proton acceptor. Next, we are going to look at, this is the last part of the notes. We are going to look at who is the Bronsted-Lowry acids and bases. So we only focus on the reactants, okay? But in order to identify our Bronsted-Lowry acids and bases, you need to look at the product, what happens to it after the reaction, okay? So I will use color coordination so that you can see. First one, H2O is reacting with a carbonate. My H2O has become OH minus, okay? I can see it already. I don't know if you can see it. CO3 2 plus has now become HCO3 minus. So you can see that the carbonate has accept the proton. That means it is a base. Bronsted-Lowry base. H2O is an acid. Okay, I hope you can see that. Next, Hclo4 reacts with CH3COOH. Now, don't be so tempted to think, CH3COOH, that is a carboxylic acid. That must be my acid. No, let's see first. HClO4 becomes ClO4 minus. We have lost a hydrogen. We have lost a proton there. Whereas the CH3COOH now has an extra hydrogen, extra proton. That means HClO4 must have been an acid, and CH3COOH was your base. Okay, so I will just color coordinate them for you again. HCl has become a Cl minus, NH3 has become an NH4 plus. Now it's your turn to decide which one is an acid, which one is a base. Next, CH3COO minus has become CH3COOH, whereas H2O has become OH minus. Okay. Question 5. HSO4 minus has become H2SO4. H3O now becomes H2O. Okay, so I'll leave the next 3 questions, question 3, 4, and 5 for you to answer. And please put in your answers to this question in the questionnaire in forms. So that is all for today. Assalamu alaikum and thank you everyone.